Hello everyone, my name is Dmitry Ursegov. I work in Postgres professional company as a technical manager and as a software engineer. I want to talk about highly efficient interconnection for distributed Postgres. This is the plan of my talk. I will start from scalability problem and the sharding technique, discuss its implementation in Postgres and what drawbacks it has now. It will be shown how the new transport may solve most of them, and finally we will discuss in short the planning and execution in distributed Postgres. Before I start, I want to tell a short story. Some time ago I had a call with my former colleagues. We discussed what everyone is doing now, and I gave a short form of pretty much the same talk. At the end, one of the guys who works on data transfer technology between databases and the cloud said that it is cool, but why do we need this? We can just run many databases and move data between them as needed. So I decided to spend some time and to talk about scalability problem in general and the importance of sharding. The database scalability is the ability of a database to handle changing demands by adding and or removing resources. The interesting moment is that it says more about maintenance and infrastructure than performance. So you need to keep in mind that maintenance is an important part of complete system, not only performance. By the way, you start to think about database scalability when your workload hits the limits of a database or hardware by one of the dimensions. The amount of data, volume of requests, or size of requests. Databases adopted a number of techniques to cope with the problem. The most famous are replication, when more servers with read-only copy of a database are added. Partitioning, when tables on a single server are divided into independent parts by some criteria. And sharding, where each such partition may be located on a separate server. This table is quite big. You don't need to dive into details, but I mostly used it for myself to make an analysis and a short conclusion on the next slide. I considered the three techniques with some variations and evaluated them in terms of impact on user application and performance of different types of queries. The short conclusion is that of course replication doesn't require to change the data model. That's nice, but it still has limited scalability, especially for big tables with hot data, analytics, and write requests. There are several reasons for this, and I mentioned some of them. For example, shared buffers with replication store the same data. Vacuum process run on a single server. Analytics queries cannot run in parallel, and storage size is limited. To some extent, these limitations can be mitigated with shared storage in the cloud. It has unlimited size, and with fast network it can give more IOPS, but we still have a single server and still limited by its CPU resources, for example. Another approach to to handle scalability on a single server is partitioning. It allows to run, for example, parallel vacuum and use memory more effective. On the other hand, if we look at sharding, we can see that it has unlimited scalability, and this is partially why I will further talk mostly about sharding. The important limitation of sharding is, of course, that it requires an adoption of the data model and queries. What actually we need to do with a model or queries? The main idea is to distribute data and queries evenly across the shards. For example, a database with documents that contains some information about country regions should be distributed by document ID, and not by region ID, because data by region is obviously distributed unevenly. Some regions may be bigger than other, and so on. Another moment that is worth noting now is that sharded transactional database efficiency depends on two aspects. The first one is the ability to build a distributed plan that minimizes amount and size of data transfers. The second is to minimize overhead of the data transfers. It's interesting that historically sharded database can be built in Postgres with partitioning and Postgres FDW subsystems. FDW is a way in Postgres to access foreign data source using regular SQL queries. In particular, Postgres FDW extension implements this interface for foreign Postgres servers. A sharded table can be built as a traditional partition table where some of the partitions are declared as foreign partitions that point to different nodes. Distributed query execution requires several capabilities from a database. As we discussed before, we discussed it before, but I decided to write them in more details here and mapped to Postgres subsystems. The good news that partitioning and Postgres FDW already provides a great foundation for distributed planning and execution. It can still be improved a lot, of course, and I even show some of the optimizations at the end. But during this talk, I want to focus on transport subsystem. It is clear that transport is responsible for transferring data, but in context of this talk, the transport will be shown as a broader concept that can be separated from transactions implementation or the model of connections and execution. First, let's have a look at the role of transport from the point of different workloads. The more data to transfer, the more transport is important. Of course, low latency queries with many short round trips and large data transfers benefit more. But on large scale, the overhead from transport in a wall become much more significant. We will look at this problem later. In short, the implementation of transport in PostgreSQL looks as follows. When you issue select like that, PostgreSQL creates a new libq connection to the remote node. It starts repeatable transaction. This is used for consistency, because even on a statement level, because even when you execute a single statement locally, it can generate several queries to the remote node. It can the simplest example is join, when you need to fetch rows for two tables, and partially the same reason is to create a cursor to fetch to make several queries through the one connection. This is the one reason, and the second is to handle results that can be fed to the memory. And also the interesting implementation detail of PostgreSQL is that it needs to deparse some part of plans of query plan to make a SQL text again and send it as usual through the libq connection. So all this implementation give us five commands that we need to execute on a remote server, and of course 5 network round trips, even if we do just a simple select on a local machine. The results of running pgbench simultaneously to all nodes give us the following results. I run two types of queries, point queries and queries that generate big size of results of big size. The overhead of sending 5 commands instead of 1 lead for point queries lead to 4 times more latency with the same CPU utilization, and as a result FDW achieves single server performance only on 7 nodes cluster. Bulk transfers work better, but still we need 3 nodes cluster to get the same numbers. We also have other issues. Each external client may produce internal connections to all of the nodes. This is because the required data may be located on any node. So any node should redirect a query to the node that store the required data. As a result, we may get m times n total number of connection in the cluster, where m is the number of external clients and n is the number of nodes. In other words, every node may finally have a total number of external connections to the whole cluster. PGBench in our test required 64 connections per node to get the maximum throughput. So for 100 node cluster, it led to 6,400 connections per node. Even worse, that network latency and application processing times will often result in a much more database connections, because most of them being idle, even when the applications are issuing database requests as fast as they can. Idle connections consume memory and generate context switches that become critical on large scale. libpq and connection model have other limitations that reduce the overall efficiency. So what we can do with this? We want to suggest a new transport and connection model that solves these issues. The architecture details are as follows. It has some similarity with the ideas from C10K problem. Each node runs a multiplexing process. Multiplexers connect with each other by a single connection. Pool of workers is used to execute internal requests, and workers and backends connect to multiplexer with shared memory queues. It helps us to reduce total number of connections in cluster a lot. We have only m plus n now, and total of processes is reduced as well. Multiplexer process just runs libv loop, and mostly just move the data between backends and workers on local and remote nodes. Messages are read from ready backends and workers, and at the end of each iteration are written to corresponding sockets in vectors. The same happens in the opposite direction. More details about workers and backends. The task of worker is also very simple. It just executes queries in a loop. The important part is that it can switch transactional contexts quickly and execute queries from different transactions on a substatement level. Workers are stateless. Transaction state is stored only on a coordinator. The node that started the transaction on the coordinator, that is the node that started the transaction. It is passed back and forth between processes. In our current implementation, we use CSN as a global snapshot that makes the state very short. Actually, it is just 8 bytes for the snapshot, to represent the snapshot. The other features are push protocol and binary representation for the results, and also fast communication between processes with shared memory queues. We use standard Postgres shared memory queue, but we replaced signals in latches with eventfd. Here are some synthetic numbers for latency and performance. The whole chain includes we send messages from backend to first shared memory queue, first multiplexer, then through TCP socket, second multiplexer, and at the end to the second shared memory queue and backend and worker, and then the worker sends answer back. As it can be seen, the results are near the hardware limits. The latency is mostly the same as pgbench select 1 or just ping localhost. Throughput can be it's possible to get 1 million messages per second if the test will be tuned to maintain queue utilization. Now just sends some number of messages and wait for to get the results from them. Let's have a look at results in PGBench. It show performance and scalability on a more or less real workload for point queries and bulk transfers. The horizontal axis shows the number of nodes and the vertical the TPS number. So we scaled the cluster up to 100 nodes. It is clear that that approach with multiplexing and fixed pool of workers scales much better. The notable result is that performance on 2 nodes exceeds the performance of a single server, and that scalability is linear to the number of nodes. We skipped some results collected for Cidus because they looked a bit strange for us. Of course, we have a to-do list. It is also incomplete, but I want to show some of the tasks that need to be solved. The first is related to the limits of a single multiplexing process. Despite the using of eventfd, the number of system calls become a limit for point queries. The same is for memcopy and bulk transfers. We still can work on performance of a single process, but obviously the next step is to look at scaling the number of multiplexing processes. Currently, cluster with 100 nodes with 10 cores each is not limited by a single multiplexing process, but we can actually scale pretty good with 16 core by a node. It will scale a bit slower, but it's still pretty good. The second story is about prepared statements. They were broken long before the multiplexing, and they require some significant time to fix them. And the last one, I guess, worth more details. I put more details on the next slide. Postgres FDW infrastructure seems the most clear place to integrate the new transport. I will show on the one of the next slides that Postgres FDW itself can be optimized to get great results, and with integration with new transport is a perfect solution together. We now working on write transaction support, and I hope that we will finish this task during the next month. As I said, that we chose Postgres FDW infrastructure because it provides great foundation for distributed planning and execution, but it still lacks many capabilities, especially for push execution. So we decided to work on them in parallel with the transport, and got some significant results. Here is the results in HammerDB. We achieved these results without new transport, and we expect 30% more when we switch to it. Also on this diagram, note that original Postgres FDW performance is marked as a black box on the Sharman bar. So the conclusion is that the new transport provides low latency and high throughput interconnection for distributed PostgreSQL. It allows efficient execution for workloads with large volume of requests or size of transferred data. Postgres FDW provides great foundation for execution and planning, and together with new transport can scale to 100 nodes and even more. The patches for Postgres FDW and sources of multiplexer extension will be available during, I hope, will be available during the next month. And for any questions or comments, you can write to my email. And thank you all.